Welcome to our latest video on the topic of aldehydes and ketones, iodoform reactions and reactions with 2,4-dinitrophenylhydrazine. This video is suitable for A-level students. By the end of this video lesson, you should understand that the reaction of aldehydes and ketones with 2,4-dinitrophenylhydrazine is an example of a nucleophilic addition, -elimination reaction, or a condensation reaction. You should also be able to explain how the reaction with 2,4-dinitrophenylhydrazine can be used to identify specific aldehydes and ketones, and you should understand that the triiodomethane or iodoform reaction is used to identify CH3 attached to C double bond O groups or their precursors. In our previous videos on aldehydes and ketones, we've learnt that aldehydes and ketones are a series of compounds that contain the C double bond O group or carbonyl group. And in aldehydes, the carbon atom of this group is joined to at least one hydrogen. So the general formula of an aldehyde is RC double bond OH, and R is shorthand for an alkyl group. Examples of aldehydes are shown here. We have ethanal, which has 2 carbons and is an aldehyde. We have propanal, which has 3 carbons, and we have butanal that has 4 carbons, and all have an alkyl group attached to a C double bond O and a H. Now in ketones, the carbonyl is joined to 2 other carbon atoms, so the simplest ketone must contain 3 carbons, and the general formula of a ketone is C double bond O, R, and once again R is shorthand for an alkyl group, e.g. a methyl group. And 2 examples of a ketone are shown here. We have propanone, which has a CH3 attached to a C double bond O and then another CH3, and butanone, which has a CH3 attached to a C double bond O and then CH2CH3. And notice that the alkyl groups can be the same as in propanone. They're both CH3 groups, or they can be different, as in butanone. We have a CH3 attached to the C double bond O and then a C2H5 group. Now in our previous videos, we've learnt that a difference between aldehydes and ketones is that aldehydes can be oxidized to form carboxylic acids, but ketones cannot. And we talked about 2 chemical tests that use that difference to distinguish between an aldehyde and a ketone. Now the first was Tollens reagent, the silver mirror test, and Tollens reagent contains silver ions surrounded by ammonia molecules and is formed by dissolving silver nitrate in aqueous ammonia. And when Tollens reagent is heated with an aldehyde in a hot water bath, the aldehyde is oxidized to the corresponding carboxylic acid, while the silver compound is reduced to metallic silver, and therefore if you've got an aldehyde present you see a silver mirror in the test tube. Now ketones do not give a silver mirror with Tollens reagent. This is because ketones can't be oxidized and aldehydes can. So that's how you can tell the difference between an aldehyde and a ketone. You add Tollens reagent, and if you get a silver mirror, it's an aldehyde. So this slide shows what the silver mirrors look like, and I've got 3 test tubes here, and there's been 3 positive tests with Tollens reagent, so there must be 3 aldehydes here, as all 3 give a silver mirror with Tollens reagent. Now the second test that we talked about in previous videos to distinguish between an aldehyde and a ketone is the Fehling's test. Now, Fehling's solution contains aqueous copper 2+ ions, and when boiled with an aldehyde, the aldehyde is oxidized by the Fehling's solution to the corresponding carboxylic acid, whilst the copper 2+ ions are reduced to copper 1 oxide, Cu2O, and copper 1 oxide is insoluble, and this forms a brick red precipitate. So Fehling's gives a brick red precipitate with an aldehyde and doesn't with a ketone, and that's how you can tell them apart. So both Tollens and Fehling's are reagents that can tell the difference between an aldehyde and a ketone, and they're both oxidizing agents, and they work by oxidizing the aldehyde to a carboxylic acid. And when these reagents are reduced, you get a silver mirror in the case of Tollens reagent, and you get a brick red precipitate in the case of Phelan's. And ketones can't be oxidized, and that's why you don't get these observations. Now, 2,4-dinitrophenylhydrazine is a reagent that will react with an aldehyde or ketone to produce an easily identifiable orange crystalline product. And the reaction is classified as a nucleophilic addition hyphen elimination, or more commonly, a condensation reaction. Now, a condensation reaction is where two or more molecules react together to form a larger molecule with the elimination of a small molecule. So, for example, water. Now, as you can see from the picture, the orange crystals that form when you add 2,4-dinitrophenylhydrazine to an aldehyde or a ketone are easily identifiable. And the reaction that takes place when 2,4-dinitrophenylhydrazine reacts with an aldehyde or ketone takes place in two stages. The first is a nucleophilic addition, and the second is an elimination reaction. And water is eliminated to form these orange crystals. So now let's take a closer look at how the reaction works. It's important to stress that you don't need to know the mechanism for this reaction for the exam. However, it is useful to understand the different steps so that you can understand why the reaction is classed as a nucleophilic addition hyphen elimination. So we're going to start here with ethanal, and ethanal is CH3 bonded to a C double bond O and a H, and this is my aldehyde that I'm going to react with 2,4-DNP, and I'm going to put in the delta plus on the carbon and the delta minus on the oxygen. Now there is a lone pair of electrons on the nitrogen that's bonded to the two hydrogens, and that can attack the delta plus carbon, and this can cause the double bond to break. Now this part of the reaction is called nucleophilic addition, and when the double bond breaks, a pair of electrons goes onto the oxygen, and the oxygen becomes negatively charged. Now I'm going to highlight the two hydrogens that are attached to the nitrogen here, because I want to show you where they end up in the intermediate. So one of these hydrogens forms a coordinate bond to the O minus that we form in step 1, and the other hydrogen remains attached to the nitrogen. Now these can join together, this hydrogen and this OH can join together to form water, and water is eliminated. So the first part of the reaction is a nucleophilic addition, and the second part of the reaction is an elimination, because the hydrogen and the OH are removed and they join together to form water. And the final product is the orange solid. And this orange solid would be called ethanal 2,4-dinitrophenylhydrazone. Now in an aldehyde and a ketone, the only thing that change each time is the group attached to the C double bond O. So in ethanal, it's a CH3 and a hydrogen that's attached. So I've circled on the 2,4-dinitrophenylhydrazone where these groups end up. And if I had propanone reacting with 2,4-dinitrophenylhydrazine, I would have a CH3 and a CH3 in this circled group. Now when propanone reacts with 2,4-dinitrophenylhydrazine, the orange solid that you get is called propanone 2,4-dinitrophenylhydrazone. So all you do is you put the name of the aldehyde or ketone first, and then you change 2,4-dinitrophenylhydrazine to 2,4-dinitrophenylhydrazone. Now this reaction allows you to identify specific aldehydes or ketones. Because when you add an aldehyde or ketone to 2,4-dinitrophenylhydrazine, you will always get an orange solid. And this can be filtered, purified, and you can detect which aldehyde or ketone you had by measuring the melting point of this orange solid. And different aldehydes and ketones produce hydrosomes with different melting points. So this reaction is a way of distinguishing between different aldehydes and ketones. For example, if you want to distinguish between ethanol and propanol, you could add 2,4-dinitrophenylhydrazine and melt the product, and then you can find which aldehyde you have from the melting point using literature values. Now these hydrosomes tend to melt at very precise temperatures, so that makes it really, really easy to identify the original aldehyde or ketone. Now note that 2,4-DNPH can only be used to test for an aldehyde or ketone. Other carbonyl groups such as esters and carboxylic acids do not undergo this reaction. Now the next reaction or chemical test that we're going to look at is the triiodomethane iodoform reaction. Now the triiodomethane reaction is a test for the presence of the following groups. It's a test for a CH3 attached to a C double bond O in an aldehyde and ketone only. And it's also a test for a CH3 attached to a carbon next to an OH in a primary or secondary alcohol. And to carry out an iodoform test, you need to warm a few drops of the compound with either a solution of iodine in sodium hydroxide or a mixture of potassium iodide and sodium chlorate. Now a positive test with this reaction gives a pale yellow precipitate, and this pale yellow solid that is formed is triiodomethane, CH3, and that's why the reaction is called the triiodomethane reaction, because triiodomethane, CH3, is formed, and this is a yellow solid that is insoluble. Now, the reason you get a positive test for both groups is that the reagents used in the iodoform test oxidize primary or secondary alcohols to form aldehydes or ketones. For example, iodine is a substance that easily gains electrons, and it's very good therefore at oxidizing primary or secondary alcohols to aldehydes or ketones. And if you have a CH3 attached to a COH, this will oxidize when you add the iodine in sodium hydroxide to a CH3 bonded to a C double bond O. So the triiodomethane reaction, the iodoform reaction, is a test for a CH3 bonded to a COH in a primary or secondary alcohol, and a test for a CH3 C double bond O in an aldehyde and ketone only. And I have to stress that only. It doesn't work for an acid chloride, it doesn't work for a carboxylic acid. It's a test for a CH3 bonded to a C double bond O in an aldehyde and ketone only. Now when it comes to aldehydes, there is only one aldehyde that gives a positive iodoform test, and this is ethanol, because ethanol has a CH3 bonded to a C double bond O and a H. So ethanol is the only aldehyde that gives a positive iodoform test. So now let's test your understanding of what's been covered in this video lesson with some practice questions. So here's our first practice question. Read for the question, pause the video, have a go at it, and then we'll go for the answers. Now question 1 is asking you to state the reagents you would use to carry out a triiodomethane or iodoform test, and then it's asking you to state the observation you would get for a positive test. Now for the reagents, there's two possible combinations you could use. You could either use iodine and sodium hydroxide or sodium chlorate and potassium iodide. 1 mark for that. And the observation would be a yellow precipitate or solid. Now here's question 1b. So once again, read through the question, pause the video, have a go at it, and then we'll go through the answers. So now let's go through the answers to question 1b. Now question 1b is asking you to complete the table below by giving any observations made or writing no reaction as appropriate when these reagents are added to the compounds listed, and the reagents are 2,4-dinitrophenylhydrazine, Tollens reagent, and iodine in NaOH. Now 2,4-DNP is a test for an aldehyde or ketone, and the first one is done for you. Butan-2-ol, there will be no reaction because it's not an aldehyde or ketone, it's an alcohol. Now the next one is ethanal, that's an aldehyde, so you get an orange solid or an orange precipitate with ethanal. And with ethanol, you get no reaction because it's not an aldehyde or ketone. And with propanone, because it's a ketone, you get an orange solid or an orange precipitate. Now for the next reagent, Tollens reagent, there would be no reaction with butan-2-ol because Tollens reagent is a test for an aldehyde and butan-2-ol is an alcohol. You would get a silver mirror with ethanal because it's an aldehyde, no reaction with ethanol because it's an alcohol, not an aldehyde, and no reaction with propanone because it's a ketone and not an aldehyde. And for the last reagent, you have iodine and NaOH, and you would get a yellow precipitate with butan-2-ol because iodine in NaOH is the iodoform test, and it's a test for a CH3 next to a C double bond O or a CH3 next to a COH in a primary or secondary alcohol. Now we have a CH3 next to a COH in a secondary alcohol here, so that's why you get a yellow precipitate with butan-2-ol. Now ethanal has a CH3 attached to a C double bond O and is an aldehyde, so therefore this also gives a yellow precipitate with iodine in NaOH. And my next compound is ethanol. Now ethanol is a primary alcohol that has a CH3 bonded to a COH, so therefore this also gives a yellow precipitate or a yellow solid with the iodine in NaOH. And the last compound is propanone. Now propanone is a ketone that has a CH3 bonded to a C double bond O, so this also gives a positive test with iodine in NaOH, and you also get a yellow precipitate or yellow solid forming. So there are 4 marks for this question, and there's 1 mark for each correct column. So if you had all the observations right for butan-2-ol, you get a mark. If you had them all right for ethanal, you get a mark. If you had them all right for ethanol, you get a mark. And if you had all the observations right for propanone, you get a mark. So 4 marks in total. So now have a go at question 2. Once again, read through the question, pause the video, have a go at it, and then we'll go for the answers. Now question 2 is all about the compound 2,4-dinitrophenylhydrazine, and the first part of the question is asking you to state the feature of this compound that enables it to react as a base. So the reason it can act as a base is it's got lone pairs of electrons on the nitrogen atom or atoms. 1 mark for that. Now question 2b is asking you to state what's seen when 2,4-DNPH is used to identify an aldehyde or ketone. Now when you add 2,4-dinitrophenylhydrazine to an aldehyde or ketone, you get an orange precipitate or solid, so it's 1 mark for that. And it's asking you why 2,4-DNPH is an appropriate reagent to use in the identification of aldehydes or ketones. Well, it's because the derivatives that you get, these 2,4-dinitrophenylhydrazones, these orange crystals, they have precise melting points which enable you to identify which aldehyde or ketone was added to 2,4-DNPH. So the derivatives formed using 2,4-dinitrophenohydrazine have precise melting points to enable identification of the aldehyde or ketone. So there's 1 mark for that. So here's our last practice question. We would like you to state which of the following compounds you would expect to undergo positive iodoform reactions. Pause the video, have a go at the question, and then we'll go for the answers. So the iodoform test is a test for a CH3 attached to a C double bond O in an aldehyde or ketone only, and it also is a test for a CH3 attached to a COH in a primary or secondary alcohol. Now if I look at the first compound, compound A, I have a CH3 attached to a C double bond O, and the compound is a ketone, so that would have a positive iodoform test. If I look at compound B, I don't have a CH3 attached to a C double bond O, even though it's a ketone. And if I look at compound C, although it's a primary alcohol, I don't have a CH3 attached to the COH. So compound C doesn't give me a positive iodoform test. And if I look at compound D, I have a primary alcohol that has a CH3 attached to a COH, so that gives me a positive iodoform test. And if I have compound E, although I do have a CH3 attached to a C double bond O, it's an acid chloride, not an aldehyde or ketone, so this doesn't give me a positive iodoform test. And if I look at compound F, I have a carboxylic acid here, and this doesn't give me a positive iodoform test. So out of these 6 compounds, A and D give positive tests. So that concludes this video lesson. So after watching this video, you should now understand that the reaction of aldehydes and ketones with 2,4-dinitrophenohydrazine is an example of a nucleophilic addition-elimination reaction or a condensation reaction. You should also be able to explain how the reaction with 2,4-dinitrophenohydrazine can be used to identify specific aldehydes and ketones, and you should understand that the triiodomethane iodoform reaction is used to identify CH3 attached to C double bond O groups or their precursors. So that concludes our video. Please check out our YouTube channel, Dr. O Chemistry, and our Twitter site, which contains lots of chemistry information and links, @Rada Chemistry.